Welcome to our project presentation for EC 551 at Boston University. Our goal was to create a legacy video game to play on an FPGA. BangBang is a game that was originally developed and played in Windows 3.1. In the game, two stationary players or cannons are trying to shoot each other by changing the angle and velocity of their cannon. The trajectory of the cannonball is also affected by random wind and steady gravity. We use the Nexus 3 FPGA board, VGA, and push buttons. Our game consists of 5 modules, and 2 have sub-modules. The user interface connects the controller and the user. By pushing the buttons, the user can send a signal to the system. The trajectory of the cannonball is affected by the speed, angle, gravity, and wind speed. The graphics driver contains the ROM memory for sprites, overlap checking, and the graphics controller. The map and background contains the map generator, erosion for when a cannonball hits the ground, and the object generator for the movement of the clouds. Lastly, the controller determines which state to be in based on the input from the user and other modules. The user interface was originally designed for use with a keyboard, but due to difficulties, we were forced to use the push buttons located on the board. A button or switch produces quick changes in the signal generated due to mechanical properties. A software debouncer is used to clean the signal. The controller or game engine is a finite state machine which consists of the following states and transitions. Here we can see the overall flow of the game and the inputs that determine which of the 3 routes to take when it is your turn. The program waits an input while the user selects the desired speed and angle. Once the shoot is pressed, a signal is sent to the graphics driver and trajectory. It then waits for one of the 3 internal inputs to occur. Now let's take a look at a pseudo example. Ready! Fire! Go! Faster! Fire! Go! Faster and faster! Angle down. Fire! You did. Let's switch gears and take a look at the finite state machine output logic. Here we can see that the controller runs asynchronously, and specifically if a reset occurs at any time, the variables will be set back to their initial state, and specifically the gen map signal will tell the other modules in the program to return to the initial state. The start or initial state occurs after a game has been won or a reset. This sets everything back to the default. The user input state continuously checks if buttons have been pressed to increase or decrease the speed and angle. The firing state signals a shoot and updates the cannon status if a collision has occurred with an enemy cannon. Each of the 3 outcomes stop the shoot signal and set their respective output. Finally, the delay state times how long to show an explosion if a cannon was hit or a timeout if a ground was hit. Here's a great example of how opposing wind reduces a first shot and helps a second shot. Here are the equations we should calculate. Our challenge is the calculation of sine and cosine. We use this lookup table to represent the cosine of angles from 0 to 85 with 5-degree steps. When we use 5-degree steps, 8 bits are enough to represent the factorial part of the value, which is actually between 0 and 1. We are using fractions, but we avoided using floating point numbers by rounding. When we multiply 2 numbers, we round down the least significant 8 bits to obtain the integer part of the number. We do not need a good precision anyway. In order to put a difference between sine of 0 and sine of 5 degrees, we represent our velocity by 9 bits, so that the sine of 5 can have an impact using the most significant bit of velocity. The calculation is done with combinational circuitry, but the values are correctly calculated because the state machine clock is slowed down. A slow clock is already required to slow down the ball movement on the screen. The turn variable indicates the turn, and the direction of the cannonball movement is selected using that variable. In order to include the effect of the wind, we change the horizontal speed of the cannonball according to the wind. X_1 is one of the many intermediate variables which are used for calculation and truncation of excess bits. The graphics driver is split up into three parts: memory, controller, and overlap check. We used IP blocks to store the images, such as dual-port RAM and single-port ROM. We used MATLAB code to generate .coe files to be used as image data. We also added an extra transparency bit for each pixel next to the original 8-bit colors. For example, the cannonball transparency bit is set to 1 for the blue pixels and 0 for the rest. The first challenge is the timing, where any discrepancy or delayed operation will cause a failure. The second challenge is to be able to show two images on top of each other while considering the priorities. For example, when a moving ball and a moving cloud coincide, the output image shouldn't be distorted. A third challenge is the detection of collision and the location it took place. If the ball hits the ground, that part of the land should be eroded. Now we go into more detail of how this is accomplished. First, the ROM address for the object is calculated, assuming that it is coinciding with the current pixel. Then the value of that address is read from the corresponding image memory, along with the transparency of that pixel. Next, the overlap module checks if the given pixel overlaps the rectangle with given index and size. In other words, we check if there should exist a cannonball on that specific pixel. Lastly, we decide on whether that pixel is visible or not. For visibility, there should be a cannonball image on the current pixel, and it should be not transparent. Moreover, we want the cannonball to be visible during the turn, which is between the shoot signal and collision. So for this, we have a bomb enable signal. Now we go on to the next step. Visibility values for all images are calculated in a similar manner, and a visibility array is obtained. According to the image priorities and image visibility, the foremost image is selected using a case X statement. Once we have the selected image, we simply assign the color output to the color value. Collision detection is part of the VGA control module. Following the flow from the top of the screen, if we are in the visible screen region, and if the current pixel belongs to the land area, we check if there is also a cannonball in the same pixel. If yes, there is a collision. Next, we examine where the collision took place. If it took place within a left cannon region, the left cannon is dead. Similar check is done for the right cannon. If the collision did not take place in any of the cannon regions, then none of them are dead, and erosion of the land takes place by setting the erode signal to 1. As we see here, the land becomes eroded when the cannonball hits the ground. When this happens, a collision signal is received from the VGA. Then a circular erosion mask is set on the map as an object. Instead of showing the object on the screen, the erosion module overwrites the corresponding pixels on the map. Throughout the game, a lot of modules need random numbers, such as object generator and map generator. For this purpose, we designed a random number generator, which is a Type 2 linear feedback shift register, or LFSR. It is composed of 3 separate 5-bit LFSR units seeded by different coefficients. At each clock cycle, one LFSR is selected as the output. This allows us to generate a pseudo-random sequence of longer period. Moreover, the modules sample the random numbers at user-dependent random times. For example, the object generator gets a sample when the turn changes, which provides further randomness. So, how are we doing the map generation? As you can see, a new random hill is generated and only the horizontal positions of the cannon are stationary. First, we decide on 6 random distances within a given range using the random number generator. The heights of the cannons give us cannon position, the X and Y coordinates of the hill top, The beginning and end distances of the hill are also random. Now, we have to connect these points. Drawing the two horizontal lines to the left and right is easy. Retaining the same height is sufficient. While drawing any pixel, we fill the land part of the pixel map with ones. The cooler part is drawing the curves. We are using Bézier curves for that. What is a Bézier curve? It is an equation that connects 2 points with a moving point, while t goes from 0 to 1. There are 2 first-order lines connected with a third one. The point on the third line gives our final curve. The problem is that the equation depends on t. When we fix the position of the middle point with respect to the others and rewrite the equation, we get a nice function of y versus x. If we mirror this, it looks something useful. And this is half our hill. We can do the same to the second curve and finalize the map. Let's take a look at how we've accomplished this with Verilog. Since the duration of deciding the distances and fitting curve are arbitrary, we used a nested state machine. The child state machines are controlled by a parent using start and stop signals. The first child state decides on the points, while the second child state fits a curve between them. The randomization is done by setting the range and waiting for a suitable random number. If the number is proper, we set the most significant 5 bits of the variable with the 5-bit random number. After all points are generated, the fit curve module first calculates the starting index of the surface for each column on the map. When calculating the curve, the module waits for the combination calculation to be completed to avoid false results. We haven't tested for maximum speed, because watching the map generation is fun. As we have seen, there are 2 clouds on the screen that move with the wind. Every time they enter the screen, their position changes, but they keep their distances when within the screen. Whenever a cloud is outside the screen, its position is randomly changed, but it remains still outside the screen. When it enters again, its vertical position and distance from the other cloud will be different. To prevent the cloud to move with light speed, we use a position counter whose highest bits indicate the actual position of the cloud. This test bench shows that we can successfully control the speed and angle by setting corresponding buttons. Map generation takes a long time, even if we remove the slow clock for testing purposes. Therefore, we had to set X to different regions on the map and completed a test for each X by checking where the land right begins and ends. Here we can see the right begins at pixel number 51400 in the map RAM. To test the overlap check module, we defined an object at 4 different locations and checked the output of the modules for different pixels. Finally, to test trajectory, we ran the test bench with different speed and angle values and observed the change in the cannonball position. God damn, I'm good.